Section 5.4, Mean, Variance, and Standard Deviation for the Binomial Distribution. In a previous section, we learned how to find the mean and variance of any probability distribution function. We found the expectation and the variance. Well, perhaps we're interested in the expected number of problems the statistics student will get correct, or the average number of children who will win a stuffed animal. Even though we are aware that these problems are from binomial distributions, we can start off finding the expected value the same way. So consider a problem where a student guesses on each of 6 true-false problems on the test. So I'm reducing it down from the 12 that we saw originally. So we're just going to assume there's 6 true-false and on the test. Well, that changes things a little bit. So instead of a probability of success being 0.2 when there were 5 different answers, if it's true-false, that means the probability of getting the correct answer is 0.5. So for each of these, I'm going to, you can think of it as setting up 6 choose, and let's say for the first one, 0, 0.5 to the 0, 0.5 to the 6th. So that comes out to 0.01563, and then I would do the same thing for the next value, 0.5 to the 1st, 0.5 to the 5th, and that comes out to 0.09375. And on down the list, this one would be 0.23437, and then 0.3125, 0.23437, 0.09375, and 0.01563. And if you've noticed already that their values tend to repeat, it's because the probabilities are half and half. So the closer the probabilities are to being 50-50, then you get this symmetry within the binomial distribution. When you have something that's more skewed, like the probability of success is 0.2 and the probability of a failure is 0.8, then that's when your probabilities tend to skew in one direction or the other. Okay, so we have this, and now we're going to use the formula for expected value to find the expected number of equations. Well, remember, e to the x is the sum of each x value times its probability. So I'm going to take each one, 0 times 0.01563, and 1 times 0.09375, and add those up. Then we have 1 times 0.09375 plus 2 times 0.23437 . Okay, so let's see what we get. And after all that calculation, I get exactly 3. Well, if you think about it, on a true-false question, if I have a 50-50 shot on every question, probably I'm going to get about half of them right. So I got 3 there. Now let's find the variance, and I'm going to use this formula, the variance of x equal to e of x squared minus e of x quantity squared. So we already found the e of x part, and all we'll have to do is square it once we plug it into this formula, but now we need to find e of x squared. And recall, e of x squared is the sum of when I take each value, square it, and multiply it by its respective probability. So we have this. And 1 squared times its probability, 2 squared times its probability, and so on for each value. Let's see what we get with that. And for that, I get 10.50008. Okay, now that's just e of x squared. That's what we found there. To find the variance, I have to subtract from that the square of the mean. So this will be, so for the variance, we'll take 10.50008 minus 3 squared, and that gives us 1.50008, which you could probably just round that to 1.5. Okay, that was a lot of calculations there. But do you notice anything? Is there another way, a faster way, to find the expected value of the variance? Well, let's look at our original numbers compared to what we found. We had that the number of trials, n, was 6. The probability of success was 0.5, but the probability of failure was also 0.5. So looking at those numbers, where do you think that 3 came from for the mean? This one might be a little more difficult to see, but where do you think that 1.5 came from? But with the binomial distribution, it's actually really easy to find the mean. So instead of going through all of that, taking each value and multiplying by its probability, for the binomial distribution, it simplifies very nicely. To find the mean, you just take the number of trials times the probability of success. And if you look back, that's exactly where that 3 comes from, 6 times 0.5. And for the variance, you take n, p, and add on that q. So the number of trials times the number of successes times the number of failures gives you the variance. Well, here if we do n times p, we found that to be 3, and then 3 times 0.5, there's my 1.5. So because we have this nice distribution with the binomial distribution, finding the mean and variance is going to be so much easier than using the previous equations we're used to for any probability distribution. And one more thing, the standard deviation, remember, is just the square root of the variance. So once I do NPQ for variance, I would just take the square root of that. So let's check it out. Let's use these quick methods now on the next problem, example 2. Scott's field goal percentage is 65%. What is the average number of field goals he is expected to make out of the next 8 attempts? What is the standard deviation of the number of successful goals? Well, for the average or the expected value, remember those two are pretty much the same. We're going to say the number of trials, 8, times the probability of success, 0.65, and that is 5.2. So out of his next 8 attempts, he's going to make about 5 of them. The standard deviation. Well, the standard deviation is going to be the square root of n, the number of trials, 8, the probability of success, 0.65, and the probability of failure, 0.35. Let's see what we get with that. You can type that in. Most graphing calculators and a lot of the 2-line scientific calculators, you should be able to type that in exactly as you see it. And I get 1.349. Much easier than doing it the long way. All right, example 3. A pharmaceutical lab determines that a new drug is effective in 98 out of 100 patients. A local physician decides to administer the drug to 12 patients she believes will benefit from the drug. A. Estimate the number of patients for whom the drug will not be effective by giving the mean of the relevant distribution, that is the expectation of the relevant random variable. Do not round your response. Let's just stop right there. Now, the way the the numbers were presented to us, we were talking about the drug being effective. But in Part A, they're interested in the drug not being effective. So we have to kind of switch our, not our motivation, but switch our perspective here. So if I'm talking about the probability that it will not be effective, that means P is equal to 0.02. And that's what I want to set up. So it's like I want to be successful at not being effective, if that makes any sense. So to find the expected value, or the mean, we would just say NP, which in this case there are 12 patients that are getting that drug, and the probability of it not being effective would be 0.2, which is 2.4. So out of 12 patients, on average, we expect it to not work with about 2 patients, 2.4. So that's Part A. Part B, quantify the uncertainty of your estimate by giving the standard deviation of the distribution. Round your response to at least 3 decimal places. So remember, the standard deviation is the square root of the variance, which is NPQ. The number of trials patients is 12. The probability of not being effective is 0.2. And the probability of being effective is, oh, it's not 0.2, my goodness. It's 0.02. So that changes things here. That's 0.24. So less than 1. So on average, she doesn't expect this to be ineffective with anybody. Okay. Caught that little mistake there. So over here, we're going to have 0.02 for the probability of not being effective and 0.98 for the probability of being effective. And that comes out to 0.485. Okay. So with the binomial distribution, once we can verify that an experiment is binomial if it's all 4 of those properties, finding the mean and variance becomes really, really easy. Just the number of trials times the probability of a success for the mean, and for the variance, NPQ, the number of trials times the probability of success times the probability of failure, and for the standard deviation, just take the square root of that.